So we are going to have to compute the Jacobians. The Jacobians come up right H and W. Right? H is the Jacobian of little h, and W is the Jacobian of F. That's awfully inconsistent. Why don't they use a big F for the little f if they're going to use a big H for the little h? I shake my fist at their nonsense. Obviously, you should be consistent when you write equations, just because people like symmetry. I like symmetry, and it bothers me when people don't do symmetry. Okay. How do you do the Jacobian? Basically, we talked about it. Yeah, you use the back propagation. If you don't remember, go watch that lecture. Okay. The one that's tricky is the observation Jacobian. Why is it tricky? Because in an ideal universe, and by ideal universe I mean in the simple way that the Kalman filter was designed, it is assuming that your observation function looks just like this, where state goes in and observation comes out. In reality, however, I have pulled a trick on you, and I have made it such that state and an x position and a y position go in, all concatenated together into one vector, and what comes out are a red pixel value, a green pixel value, and a blue pixel value. And then I sweep across the entire image 64 by 48 times, and I call this function for every pixel in the image in order to generate the pixel for that image, and that produces my observation. Do you see that this function can accomplish exactly the same thing as this function? Okay, but now it's tricky right here in the Kalman equation because, no, right here, because you need h, which is the Jacobian of the observation function, but there is no observation function in the form that you're thinking of. So given that you only have this function and you know how to compute Jacobians, where are you going to get the Jacobian of that function? Same thing, you sweep across it. Okay. That problem was really hard to describe, and the answer was really dumb, wasn't it? I'm sorry. That was it.
So
you got it.
you forward prop across
yeah.
Jacobian matrix.
So let's talk about what that looks like. What is the size of your observation here? Meaning the full-blown observation.
How many pixels?
There's 64 by 48, and there's 3 color channels. So 64 times 48 times 3. There's 9,216 dimensions in this vector that represents that picture of the crane in this observation.
We have a square matrix where each dimension is 9,000.
Yeah, now if we look at the Jacobian matrix, we see that for every output dimension, there's a row, and for every input dimension, there's a column. How many input dimensions do we have in this function right here? 2. So your Jacobian matrix H is going to look kind of like this, where this is a 9216 and this is 2. And we need to fill in all of the values of that matrix. And how are we going to do it? Well, for each pixel in our observation function, we're going to end up calling this function. And we're going to get the x and y position that we want. And we're going to do forward prop to compute the RGB values. And then we're going to add 1 to one of those columns. So we can say, how will that one change if I adjust my input? And then we'll do back prop, and it will tell me how all 3 of these values change. Excuse me, all 4 of those values. There's actually 2 elements in state here. So there's 4 inputs going in. Just so I'm a little less confusing, let me call this state 1 and state 2. There. Okay, so I'll forward propagate, I'll get the RGB. So I'm actually going to have to do it 3 times for every pixel. I'll add 1 to one of those elements. or some other number if you prefer. Then I'll do backprop, and it will tell me how each of these 4 elements changes on the tangent hyperplane when I change the y by that much, because we're doing the tangent hyperplane, the gradient, right? The ratio between those two is precisely this ratio in the Jacobian matrix, because it's how much does y change when x changes, right? Okay. But what's interesting is I've got 4 input values, not 2. What do I do with those? Yeah, throw 2 of them out, because while yes, it's telling me I could change my state in order to get different outputs, I don't care. I only want to know, wait, no, that is what I want to know. I could change the pixel I'm looking at in order to get different outputs, but that's not interesting to me. That's not what I want. I only want the 2 states. So throw out those 2 values, and the other 2 are still the correct ratio between if this part of the state changes, how does it change that portion of the pixels. Specifying them here doesn't actually change the way math works. It's still true. Does that click with you? Does it ring right? Or do you need a little more proof before you're content with that? So yes, you will have to run through 90,092 once. You'll have a loop that'll visit 9216 different spots. And you'll end up calling forward prop and back propagate that many times. And you'll do this every single iteration, every single frame of this crane simulator. Sounds friggin' slow, doesn't it? Well, modern computers are friggin' fast, so you're good. And here's how I know that. See how I'm driving this around and it looks nice and speedy? Well, I'm doing forward propagate for every single pixel in this thing just to get that image. So you're going to do a forward propagate and a back propagate for every single pixel in that image. So at worst, you'll slow it down by a factor of 3. Because I'm doing one thing and now you'll be doing 3 things. Plus all the other math in the Kalman filter. That'll slow it down even more. So yeah, maybe you'll end up being 10 times slower than this. But this is already fast enough to keep up with the delay between frames that I did. So I frankly don't think you're even going to hit it. And if you do, oh well. This class isn't about performance, it's about math, so you'll be fine. In other words, for some reason, whenever I code with loops, I feel like I'm doing something harder than when I'm just writing the math straight out, even though it's really the computer that's doing all the hardness. Don't feel bad, just use a loop, and it doesn't get any harder. Okay? So we know how to do that Jacobian, and we know how to do this Jacobian, because we've talked about that before. I think you can code that up. And finally, I just want to make sure you know what we're doing. As we go through this loop, we're doing a bunch of math, obviously, but what does it mean? The main thing we're recomputing is x and p, right? So we started with an x and a p, and it goes in and goes through the loop, and we just keep updating x and p. Every time we do an action, we get a new observation, and we say, here's the action I did, and here's the new observation I see, here's the new x, and here's the new p. And they're both going to just keep on updating. And what we're doing there is we're tracking where we believe the state is, even though state is never given to this thing. And that's only mostly true. It actually is right here. But this isn't the real state. This is the belief about state. Turns out we're going to give it the true state for the very first iteration because why not? Something to do. But yeah. So what should your initial P be?
Should be the noise value that you give scaled by something.
Yeah, I guess I'm going to say it doesn't really matter because whatever you give it, it'll converge to what it should be eventually. So how about for starters, let's just start with saying we know the truth. We'll give it the true x, and p will just be a whole bunch of zeros. I think that works. Yeah, that'll work. So we'll just do that. And it'll still get uncertain because there's still noise, and it still doesn't know the truth because there's still transition noise and observation noise. Okay. And we're going to represent that it has computed those values by drawing crosshairs. I say just a little plus. If you make a circle around the plus, that looks cooler. For C++, there's not a great SDL function that draws circles. That bugs me. You can write one if you want, or just draw a box, or don't, just use crosshairs, whatever you like. But there should be a circle function. It's really easy to write circles. Do you want to know a really efficient way to draw circles? What do I got? I only got 2 minutes. That's perfect for this. So you can draw a circle without ever doing a square root. That's the trick to making an efficient circle. So imagine that there's a circle here, and you started right here, and x, let me do it this way. This is a computer graphic thing, not a, I'm done with my lecture right now, so I'm just showing you something. Imagine you wanted to draw this circle, and you were at this x position. You're right here. And then you add 1 to x, and you add 1 to x, and you add 1 to x. The only thing you really need to know is when does y increment, right? And if you could draw up to there, 1/8 of a circle, everything else is symmetric. So you really just need a loop that's going to compute when y increments from there to there. And the trick is to keep track of the square of the distance. And you say when, let's see, what is it? When the amount that x has moved is more than the square of, it's not coming to me right now. I need to brush up on things before I lecture about them. Oh, it's just a simple distance. You just say when your distance to the radius is more than the square, when your square distance to the radius is more than it should be, which can also be computed as a squared distance, then it's time to pull y down a notch. And if you just keep doing that, it'll follow around that first quarter circle. And then you just use symmetry to simultaneously draw the corresponding points at the symmetric locations as you go around. And as you do, you complete the circle, and you can draw a circle really efficiently. So if you really want to write an SDL function that does it, now you can. Okay, there's that. Anything about the Kalman filter that you feel scared about coding up, or is it pretty straightforward now? Okay. Well, you won't know until you hit the code, and then all of a sudden it's going to be a nightmare for you, right? That's the way it always is. Sorry. But I hope it's crystal clear in your head now so you can start coding it up. If not, please do start coding it up so you can ask questions and have plenty of time to work on it as needed. And I guess that's my lecture for today, so thanks for coming.